Limit and algebraic approaches. Graphs are very useful tools for investigating limits, especially if something unusual happens at the point in question. However, many of the limits encountered in calculus are routine and can be evaluated quickly with a little algebraic simplification. Some intuition and basic properties of limit. The following list of the properties of limit forms the basis for this approach. So let f and g be two functions and assume that limit when x goes c f of x equals L and limit x goes c g of x equals M. The limit of the g of x when x approaching c is M, where L and M are real numbers. Both limits exist, in other words, okay? Then first one, limit of the constant function, which is key, when x approaching c is not important here, always is correct, equals q. So for any constant q. Second one, the identity function, limit of the identity function, which is x, as x approach c equals c. From the graph you can obtain easily this result. Basically you can see. Third one, limit of the summation of the f of x plus g of x as x approach c equals limit of f of x as x approach c plus limit of g of x as x approach c. In other words, since the first limit is L, since this limit is L, that is L, and this is M, so this is M, so that summation equals L plus M. And similarly, we can say that a limit of the f of x minus g of x equals limit of the f of x as x approach c minus limit of the limit of the function g of x as x approach c. So the differences of the limit equals limit of the difference of the function equals differences of the limits of the functions, okay? And the fourth one, scalar product. Limit of the function k times f of x as x approach c equals k times limit of function f of x approach c. Since limit is L, this is k times L. Here, k is any constant. For any constant q. Next property is 5. Limit of the product of two functions f of x times g of x as x approach c equals product of the limit of these two functions. So limit of f of x approach c times limit of the function g of x as x approach c. So this is L times M. And the next property is the division limit with the quotient of to f of x over g of x as x approach c equals limit f of x approach c over limit of g of x approach c. But here you should be careful. The limit of this limit have to be different than 0. That means m different than 0. So this equals L over m if m is different than 0. Otherwise, that quotient is not logical. This quotient is not logical. For example, 2 over 0 is indefinite, okay? And the last one, limit of the function nth root of the f of x when x approach c equals nth root of the limit of the function f of x as x approach c. So this is nth root of the L if L bigger than 0 or n is odd. So what the meaning of this restriction? If L is positive, n can be odd number. There is no problem. So even number. L can be even number. If L is positive, there is no problem. L can be even number. For example, any number. If L is negative, n cannot be even number. For example, if L is -1 and n is 2, -1 square root is not definite, so it is not possible. So either L bigger than 0, if L is negative, n have to be odd number. The second case, I asked this one, okay? If L is negative, n have to be odd number. Otherwise, you cannot use this formula or these properties of the. In your textbook, you can find some example. And as a result of this example, simply we can say some things. A limit of the polynomial f of x when x approach c equals the function value, okay? Actually, it's related to the continuity of the polynomial, but as a theorem which is given in your textbook. So, as a theorem, first part, limit of f of x as x approach c equals f of c for f any polynomial function. To prove this fact is not difficult, okay? Quickly I can give the proof for it to you. Small proof. You can find all the details. So f of x is if f of x is polynomial, it is in the following form. a1x plus a0. So if you use all these properties, product rule, scalar product rule, summation rule, etc., and also this two limit idea, you can say that the limit of f of x when x approach c equals an times limit x approach c x to power n plus, of course, by using the several properties. Here we use a scalar product and the product of two functions, okay? And similarly, an plus, and also using the summation rule, limit x goes c, x to power x equals x to power n minus 1, outside let's write, to power n minus 1 plus blah blah blah, a1 limit x goes c x plus limit a0 when x going to c. So again, by the first two properties, second property says this is the c to power n. So an times c to power n plus an minus 1, not plus 1, sorry. This is minus 1. Minus 1 c to power n minus 1 plus blah blah blah. a1 c plus a0. This limit is c, so a1 times c. This limit is a0 because it is constant from the first properties. So we obtain this fact. Actually, right hand side of the equation exactly equals f of c. So we obtain the this result. And the second part of this theorem, limit of the function r of x as x approach c equals r of c for r any rational function. As you know, rational function has the quotient of the two polynomial function. So for denominator we have to some restriction with a non-zero denominator at x equals c. Why? R of x, okay, let's write small proof again. So R of x equals numerator of x over denominator of x. So limit x approach c, r of x equals, since n is polynomial, here both of them are polynomial, equals limit when x goes c n of x over limit of denominator when x approach c. So since numerator and denominator are polynomial, numerator of n of c, denominator is d of c if d of c or the limit different than 0. Limit x goes c d of x different than 0, we can write this way. And the left-hand side is the r of c. So under this assumption, with a non-zero denominator at the x equals 0, so under this assumption, we obtain the this result, r of c with a non-zero denominator at x equals c. Why? Because this limit equals d of c. So hiddenly d of c is different than 0. So non-zero denominator x equals c. Actually, when applying the quotient rule, we said that the limit of denominator should be different than 0. That's right. But, let's look to that definition here. But if this is 0, what we can do? If this is 0 and this is different than 0, limit does not exist. But if both of them are 0 at the same time, we have an indeterminate form. Okay? So, let's write definition. Indeterminate form. So, if limit when x goes c, f of x equals 0, and limit g of x equals 0 as x goes c again, then limit of f of x over g of x as x approach c is said to be indeterminate. Or more specifically, a 0 over 0 indeterminate form. The term indeterminate is used because the limit of an indeterminate form may or may not exist. Okay, in the future you will see sometimes this limit will exist, sometimes this limit does not exist. And for the easy calculation after learning derivative, we will have a L'Hopital rule, but you don't know now. But in the future you will. Here, the expression 0 over 0 does not represent a real number and should never be used as the value of a limit. You cannot say the limit is 0 over 0, okay? This is not the correct answer for the exam. If a limit is a 0 over 0 indeterminate form, further investigation is always required to determine whether the limit exists and to find its value if it exists. If the denominator of the quotient approach 0 and the numerator approach a non-zero number, then the limit of the quotient is not an indeterminate form, okay? In fact, in this case, the limit of the quotient does not exist, as I said before, okay? So, let's state this situation as a theorem. If limit of f of x equals L when x approach c and L is different than 0, and limit of g of x when x approach c equals 0, then limit of f of x over g of x as x approach c does not exist. In the lecture, you will see generally we use this notation instead of to write does not exist. So how you can calculate or how you can do the furthermore analyzed investigation for this situation, the 0 over 0 indeterminate form situation, this situation will be discussed in the lecture time, okay? So by simplifying some common factor, we can overcome this problem. In the future, for more complex function, you will see we have some different investigation techniques to solve this type of the problems.